Hi, my name is Dibya Ghosh. In this video, I'll be talking about an operator view on policy gradients. This is joint work with Marlos Machado and Nicolas. In this work, we introduce a new interpretation of policy gradient methods, as repeatedly applying an improvement operator, which transforms a policy into a strictly better policy, and a projection operator, which takes this improved policy and maps it back into our function class of realizable policies. Through this view, we'll present some interesting consequences of policy gradient methods, including how fast policy gradient methods improve policies, how policy gradient methods interface with function approximation, and how existing policy gradient algorithms like MPO and PPO fit in this framework. If we take a bird's eye view, both policy gradient methods and value-based methods have been very successful empirically in RL. On the theoretical side, though, there's a prominent divide. In contrast to policy gradient methods, value-based methods enjoy a comprehensive theory. And part of the success in analyzing these methods is the use of operators to describe the algorithms. The most famous operator here is the Bellman operator, which maps a value function to a better value function using next time step predictions. Operators standardize a lot of the basic questions we ask about value-based methods, such as when they converge, how fast they converge, to what they converge, and more. In this work, we build an analogous view for policy gradient methods with similar operators, in the hopes that it allow us to better understand policy gradient methods, relate them more closely to value-based methods, and gain insights onto how they work and how to improve them. Policy gradient methods try to find a good policy by directly performing gradient ascent on the desired objective with respect to the parameters of our policies. Now, because these are just performing gradient descent on some objective function, the dominant analysis tool to date has been to use optimization theory to show that gradient descent converges to a local optimum. Unfortunately, in reinforcement learning, the expected return objective J can be highly non-convex, with multiple local optima, and a simple gradient descent analysis explains very little as to how these algorithms work. To derive a different view, the operator view, we take a fresh look at the exact policy gradient update. When we take the derivative of the expected return by performing the reinforce trick and the policy gradient theorem, we can show that the gradient update can be expressed in terms of three quantities: the log probabilities of my policy, the Q function of my policy, and the distribution of states and action that my policy visits. What we're going to do is interpret the second two terms together as a reweighted probability distribution that takes states and actions from my current policy and increases the weights of states and actions with higher Q values, and decreases the weights of states with lower Q values. To make sure this object is a well-defined probability distribution, we have to make a slight technical assumption that all the rewards are non-negative. But this can be dealt with in practice too. When we use this new reweighted probability distribution, the policy gradient update simplifies very nicely into the gradient of the KL divergence between the reweighted policy pi prime and the current policy pi. And through this simplification, we can say that the policy gradient update takes a single gradient step to minimize the KL divergence between itself and an improved version of itself. This is to say that we can decompose the update into two steps: an improvement step and a projection step. Now, it may not be clear on first sight that what I'm calling an improvement step is actually an improved policy, but we show that this is indeed true. And a good intuition to understand why is that this new policy increases the weights of actions that lead to high return, that have high Q value, and decreases the probability of actions with low Q values. Now, reinforce takes only one gradient step towards minimizing this KL. A natural extension, which we call operator reinforce, does the full projection. That is, it's the composition of two main operators. An improvement operator, which reweighs my policy by the Q values to create an improved policy, and then a projection operator, which finds the closest policy in my space in terms of the KL divergence. We analyze this algorithm in great detail in the paper. It turns out the operator version of reinforce is very similar to the original policy gradient algorithm. It has the same convergence points, and it maintains the nice property that every step of the way, the return increases. Now, by moving to the operator view, we gain more. We gain this flexibility in understanding how these algorithms work. We can ask what happens when we change the improvement operator, or what if we change the projection operator? Or looking at other algorithms like PPO, we can ask how their operators correspond to the operators for the traditional policy gradient algorithm. To provide a teaser for what the operator view enables us to analyze, I'd like to highlight one example regarding reward transformations in RL. Now, the improvement operator that we used to derive the policy gradient update reweighted actions by the exact Q values themselves. Now, this has the desired effect of increasing the probability of these good actions that have higher Q values. It leads to a natural question. Can we try to increase the probability of these good actions more aggressively? For example, if we instead multiplied by a power of the Q value, then the higher Q value actions are going to be upweighted more, and the policy will shift more rapidly towards these good actions. And this leads to a spectrum. On one end, when k equals 1, we have the standard policy gradient update. On the other hand, when k equals infinity, and we always choose the action that has the highest Q values, we retrieve the greedy Bellman update. And what this view allows us to do now is to bring policy gradient and value-based methods together on this spectrum. The two paradigms are really just two sides of the same coin. What happens when we use this new operator? In practice, while higher values of k, which select these good actions with more probability, lead to faster training, but after training, they converge to a suboptimal policy. And the reason that they're converging to a suboptimal policy is a simple mistake we made here. While we changed the improvement operator, we kept the projection operator fixed. To use this new aggressive improvement operator, we need to change the projection operator. Instead of the KL divergence, we need to use an alpha divergence with an appropriate value of alpha. And when we make the improvement and projection operators consistent, we get the best of both worlds, both faster learning and convergence to the optimal solution. Now, reward transformations are only one of the potential applications of the operator view. Some others that we analyzed in the paper, but haven't discussed yet in this talk, include connecting imitation learning algorithms with policy gradient methods, and how these ideas can scale to systems like StarCraft, ways to interpret the role of entropy regularization in policy gradient methods, and towards understanding our performant algorithms like PPO and MPO, understanding how their operators compare to traditional policy gradient operators. We hope that the operator view provides a starting point to interpret and derive more principled and performant policy gradient methods. If you're interested in learning more, please check out the paper on arXiv. And feel free to stop by our poster at the Theoretical Foundations of RL workshop at ICML. Thank you for listening.